Hi. In the cloud, customers often rely on hundreds of accounts in virtual private clouds to segment workloads and expand their footprint. This level of scale creates challenges around resource sharing, inter-VPC connectivity, and on-premises facilities to VPC connectivity. In this presentation, we will discuss some solutions to solve those challenges, and then we will walk through how to scale your cloud network to infinity and beyond. My name is Lightfoot. I'm a developer advocate at AWS. Let's begin with today's agenda. Now, one thing I want to mention before we begin is that it's important to understand the infrastructure first before we automate it. With that being said, we will begin today with an intro to the multi-VPC network infrastructure. Then we will discuss how to provide connectivity between our VPCs with VPC Pairing and then the AWS Transit Gateway. After that, we'll do a quick overview of Terraform, and lastly, we'll go into our demo to deploy a full hub and spoke architecture with Terraform. Let's level set. What is an Amazon Virtual Private Cloud? An Amazon Virtual Private Cloud enables you to launch AWS resources into a virtual network that you define. This virtual network closely resembles a traditional network that you will operate in your own data center, with the benefits of using the scalable infrastructure of AWS. Now, when customers first get started with AWS, the question is often, should they begin with a single VPC or many VPCs? To answer this question, the number of VPCs a customer owns is often related to the number of accounts, users, and staged environments like prod, development, or test. And as their cloud usage grows, the number of users, business units, applications, and regions that a customer interacts with also grows, leading to the creation of new VPCs, which leads to a question of, how do I build something like this? How do I go from one VPC to a multi-VPC design? And what are some of the considerations of how many VPCs? So let's take a moment to talk about how that conversation goes. That conversation is really about, should I have larger VPCs and larger accounts? Or should I have smaller VPCs with smaller accounts? And let's take a look at this. With the larger VPCs and larger accounts, you will have less accounts to manage as well as less networks to set up. But with the smaller VPCs and the smaller accounts, you'll have more accounts to manage as well as more infrastructure to set up and maintain. So if you have multiple accounts, you may have a VPC in each of those accounts. Now, with the larger accounts and larger VPCs, you can provide tighter controls within the account or VPC. And you can do this by leveraging identity and access management, or IAM. You can provide strict security groups as well as routing controls. And then you can identify resources with tags. With your smaller VPCs and smaller accounts, what you'll want to do here is provide tighter controls of provisioning and standards. You may want to leverage automation to provide standardization of things like your subnets, your routing, direct connect, and VPNs. With your larger VPCs and larger accounts, billing and ownership can become complex. Versus with your smaller accounts, each account can have its own individual billing. And with your larger accounts, it's a larger blast radius. An example would be a developer modifying your DNS of a production API that leads to a production outage or downtime, and then that affects your entire deployment. Rather than with your smaller account, that blast radius may be smaller, which you could mitigate that blast radius. Now that we have covered some design considerations for one-to-many VPC, let's take a look at some options for establishing our VPC to VPC connectivity. By default, AWS provides network isolation between VPCs. And the simplest way to connect our VPCs is by using VPC Pairing. A pairing connection or VPC pairing connection is a point-to-point network connection between two VPCs that enables you to route traffic between them privately using IPv4 or IPv6 addresses. Now, I mentioned point-to-point, that is a single point-to-point connection. You can create a pairing connection between your own VPCs with a VPC in another AWS account or within a VPC in a different region. VPC pairing utilizes the concept of requester and acceptor. Once the requester creates the request, the acceptor then accepts the request, and at that point, the pairing connection will be created. Now, once the pairing connection has been created, at that point, you will need to configure routing in both VPCs to have bi-directional communication, along with your security groups for access. Something to note is that VPC pairing does not support transitive routing. So what does this mean? This means that if you want to enable routing between VPC B and VPC C, you must create a unique VPC pairing connection between both VPCs. Now let's take a look at some VPC pairing things to know. You can reference security groups from the peer in the same region. You can enable public IPv4 DNS hostname resolution to return their private IP addresses. You can pair both IPv4 and IPv6. Some things you cannot have is you cannot have overlapping IP addresses when trying to create VPC peers. You cannot have multiple peers between the same pair of VPCs. It's a single one-to-one, point-to-point connection. And you cannot have jumbo frames across inter-region VPC pairing. Now, VPC pairing solves the challenges of connecting one VPC to another VPC. What happens when we need to expand beyond that? To help with this, we have the AWS Transit Gateway. So what is a transit gateway? Transit gateways are a regional network transit hub that you can use to interconnect your VPCs and on-premises networks. With the transit gateway being your network hub, spokes are attachments that you attach to your transit gateway. Some of those attachments being VPCs, VPN connections, and direct connect gateway. You have the ability to leverage intra and inter-region pairing of transit gateways, giving you the ability to create a global network. By using the transit gateway, you now can simplify your network connectivity and remove some of the complexity and restrictions of the VPC pairing. Something to note is that the transit gateway does not scale with traffic. We provide a quota of 50 gigabits per second per attachment. Now, before transit gateway, here's how things will look. In order for each VPC to communicate with each other VPC, you would need to establish a full mesh, which means a pairing connection between each VPC. In this example, we have 6 VPCs. That means we have a total of 15 pairing connections. Now imagine if you had 50 or 100 VPCs. You will quickly find out that managing point-to-point connectivity across many Amazon VPCs can be operationally costly and cumbersome. Now, to solve this challenge and to scale, we can use the transit gateway, which acts as a network transit hub that controls how traffic is routed among all of the connected networks, which acts like spokes. And we'll see some of this in our demo here shortly. Now that we have covered the basis of our infrastructure, let's do a quick overview of Terraform. Terraform is an infrastructure as code tool where you can describe infrastructure and then deploy that infrastructure to the cloud or on-premises locations. In this demo, we will deploy to AWS. Terraform builds a dependency graph of all of your resources and maintains the state of all your resources. And it is supported by 200 plus AWS services. Now, out the box, Terraform cannot interact with an API like the AWS API. Terraform relies on plugins called providers to authenticate and interact with cloud APIs or other infrastructure platforms. Using the Terraform provider allows you to send backend CRUD calls to create a resource like a VPC. In this example, we create a VPC resource called main. We can also gather data. Here we have a data source where we gather an IP address block from IPAM, and then we pass it to the VPC resource to be applied when the VPC is created. The last thing I want to cover before our demo is modules. Modules are an opinionated grouping of resources. This allows you to write reusable configuration files. It also allows you to use existing modules from local directories and from remote registries like the Terraform registry or GitHub. In this example, our module source is the AWS VPC module that exists in the Terraform registry. This module builds a VPC with public and private subnets and 3 availability zones. The benefits of using a remote module is that often the module is written, we can just pass in the variables rather than having to write all the codes ourselves, which practices the dry principles of not repeating ourselves in our code. Now that we have completed our overview, let's deploy a full hub and spoke architecture with Terraform. Okay, now that we're in our demo, we are in Cloud9, which is an integrated development environment on AWS. The benefits of us using Cloud9 is that we can use our IDE directly from the browser, as well as it leverages an EC2 instance that's on AWS that comes pre-installed with everything we need to develop in Terraform. It also provides us authentication to AWS. So that way we don't have to put personal access tokens inside of our provider. So now that we're in our code or our repository that we'll be using today, the first thing we want to do is take a look at what's in it. Well, here we have a main.tf file, and this is where we'll put all of the modules and resources that we'll be deploying to AWS. The architecture that we'll be deploying today is going to be the hub and spoke architecture that we mentioned from our presentation, and it will have a centralized shared services VPC for things like our VPC endpoints. I think it's important that we actually take a look at that. So let's do that now. So here we have our spokes, which is going to be VPC A and spoke VPC B. Now, for those of you that may not know what VPC endpoints are, VPC endpoints are powered by Private Link, and they provide a private connection between your VPC and another AWS service without having to go over the internet, VPN, or direct connect. So in this example, in both VPCs, we have private subnets with EC2 instances, and then we are attached to a transit gateway. The transit gateway has 2 route tables. It has a spoke VPC route table that has a route to our shared services VPC. And then it has another route table for the shared services VPC to be able to send traffic to our spoke VPCs. Now, inside of our shared services VPCs, we have VPC endpoints for SSM, Amazon S3, as well as we have resolver endpoints for our inbound and outbound DNS requests. Now, the benefits of this architectural design that we'll be using in this demo is that we get to centralize the AWS Systems Manager for accessing our EC2 instances. Normally, if you don't use a centralized VPC, what you'll have to do is add VPC endpoints in each of your VPCs. And here's an example of what this will look like. So each VPC A and VPC B would have these 3 endpoints in each VPC. And that can be hard to manage due to policies that you would have to apply to those VPC endpoints. And so our architecture that we'll be deploying today will solve this. Now, let's go take a look at our code. Now, back in our Cloud9, let's start with our providers.tf. One thing to note is that I mentioned that we're using Cloud9. So that means that we don't have to put all of our authentication information into the providers.tf. So here what we're going to do is pass in the regions that we'll be utilizing. We'll leverage the variables.tf, so that way we don't have to modify this providers file. We just simply modify the variables.tf file. And it also has the version of Terraforms and the version of the AWS providers that we'll be using. Now, if we go to our variables.tf, this is important to understand. This allows us to use our reusable code in our main.tf file more efficiently. So rather than modifying our modules in our main.tf, we can use the variables.tf file. And in this example, we have the AWS region, and we're going to deploy this to US West 2. And we'll save that. The identifier, this is going to be used for our tags. We'll pass this information in, and this lets us know that this will be for shared services. And then we have our variable.vpcs. This is going to be a map or something like a dictionary in Python to where we have multiple maps that we can pass in. So in this example, we have VPC information that we'll utilize to pass into our VPC module when we create it. So here we have a VPC1, which is going to be our spoke, our first spoke, the solder block of the spoke, the subnets that we'll have for the VPC, and then the subnets inside of the VPC that will be used for the transit gateway. So here's where we'll deploy our things like EC2 instances. And then the number of AZs or availability zones that we'll be utilizing. In this example, we'll just use one, as well as the instance type. And we'll also want to utilize flow logs, so this is information for that as well. And then we repeat this information for each additional spoke that we want to add to our variable file. This makes it real efficient when you're using modules to have that reusable code. Now here we have our on-premise solder block if we're connecting to on-prem. And then we have forwarding rules for DNS. Next, we'll look at our locals.tf. In our locals.tf, this is going to be for when we want to use more dynamic locals rather than variables. Variables are just for inputs. Locals allow you to do some really cool things for, let's say, creating security groups. If you have a different amount of security groups that you want to utilize, in this example, we may want to add a new rule. Locals is great for that, as well as we can utilize VPC endpoints. So we'll pass this in as a local when we're creating each of our VPC endpoints, because we may have multiple and we may want to use information from different places, so we can do that with a local. Now let's take a look at our main.tf, what we'll be deploying today. The first resource that we have here is our transit gateway. The transit gateway will be created, and then from there, we'll create each VPC that's in our variables.tf file, and then we'll attach it to the transit gateway that we just created. And we'll repeat this process for each VPC that's inside of our map inside of the variables.tf. We'll also be utilizing a compute module, which is going to be local. This local module will create and launch our EC2 instance inside of our subnets that we create inside of our spoke VPCs. Now, I mentioned this is the local module. The module that we'll be using for our spokes is going to be the AWS VPC module that's hosted on Terraform. I'll have more information for that at the end of this presentation, but this module is a remote module that has everything we need to create our VPC. Now, once our VPC is created, we launch our EC2 instances into our subnets. We provide an instance profile to allow us to have access to SSM once the SSM is created inside of our shared services. And then I commented out the code for the shared services. We'll look at that once we deploy our code. So let's go to our terminal. I'll pull our terminal up here. And for our terminal, the first thing we want to do is enter into our directory. And now what we want to do is initialize our Terraform modules and providers. So we'll go Terraform init. And at this point, all the backends that's needed to connect to AWS is being loaded. All the modules, everything, the remote repositories all of that configuration is being loaded. So when we do the Terraform apply, we can deploy to AWS with no issues. So I'll go ahead and clear my screen. It looks like that was successfully initialized. We'll clear. The next thing we need to do is the Terraform apply. This will apply our plan to AWS. So we'll apply, and it's going to ask us if we're sure we want to do this. And once it does, I'll click yes. And I'll enter yes, verify that it is 40 resources in our plan. And notice these are our spokes. It has spoke 2, and it's reading this information directly from our variables.tf file. And we'll press enter. So now at this point, our resources are being deployed to AWS. This takes a couple minutes, so we'll wait for this, and we'll take a look at our module for the VPC module on Terraform. Now, the benefits of using the AWS VPC module is that this module has been created and will be maintained by AWS. So you know that you're getting the best practices when you're using these modules. I think our provider and our deployment should be done on AWS, and it looks like it is. So notice that our apply is complete and we have 40 resources created. So at this point, what we will do is go to our correct region, which the region that we deployed in is going to be US West 2. And then we will go to our VPC console and notice that we have 3 VPCs, 1 VPC being the default VPC, and then the 2 spoke VPCs that we created. Now with these spokes, we should have 2 subnets for each. And notice that we do. We have a Transit Gateway subnet and a workload subnet where we launch our EC2 instances. Now let's go back to EC2 and verify that our instances has been launched. And it looks like our instances are being initialized now. They have been launched. So I think this is a good point to install our shared services VPC. So let's do that. Now, if we take a look at our module, notice that the source of our module is going to be the AWS Network Hub and Spoke module. This module is also hosted in the Terraform registry. The good thing about utilizing this module is that it does the Transit Gateway Hub and Spoke architecture, but you have several options of deployment if you utilize this module. The one that we're using today is going to be a shared services, but you can also do an inspection architecture, which are inspection VPCs, egress architecture, and ingress, as well as your hybrid DNS, which we're kind of utilizing some of that in this as well. So if we go back to our code, now we're passing in everything that we need to create our shared services VPC. And here, notice that we enter our central VPC information here with the CIDR block. Now we have our subnets, and then from there, the VPC flow logs. And then we attach our central shared services VPC to the Transit Gateway. That way we can route in between each of the spoke VPCs and the shared services. And then down here is where we create our VPC endpoints for SSM, as well as Route 53 for our DNS. This is going to be our private hosted DNS, so that way we don't have to worry about maintaining DNS in each of our VPCs. We can simply maintain this in our shared services rather than each VPC. And so from there, we're using a encryption key in KMS in order to encrypt our VPC flow logs. And that's pretty much all the code here. I will be sharing this out in our GitHub link at the end of the presentation. So please bear with me while I deploy our infrastructure. Now, before we can actually deploy, the first thing we need to do is initialize this module. Since we uncommented it, now we have to pull down all the backends that are needed in order for us to deploy. So we'll do another Terraform init. And notice that everything we need for Route 53 is being pulled down. And now we should be good to go with that. Now we will do a Terraform apply. We'll enter yes. Now this takes a few minutes because what we're doing is not only creating the shared services VPC, but we're creating all of the VPC endpoints inside of the shared services VPC and also attaching that shared services VPC to our transit gateway with all the needed routing that needs to be updated. And so once that happens, I think the longest part of this demo will be applying those VPC endpoints for things like Route 53. So we'll wait on that, and once that completes, we'll test our network connectivity to our EC2 instances. And actually, we should test that now. So let's try to connect to our EC2 instances. So while this is deploying, let's try to connect to our Spoke VPC1 instance. Notice that when we try to connect with Session Manager, it's just timing out. And that's because our VPC endpoints have not been created. And so once those are created, then we will be able to connect from the AWS console through Session Manager. And I mentioned this does take a while, so notice that our endpoints are being created. Looks like the transit gateway route table is being updated. We're being associated our subnets to the transit gateway route table. Okay, it looks like our resources have been deployed to AWS. Now, if we go back to our EC2 instance, the simplest way to test this is to see if we are able to connect through SSM. So we'll click our Spoke VPC1, click connect, and notice that we are able to connect to our new EC2 instance that we created inside of our Spoke VPC. And we can verify our IP address of that Spoke. And this is inside of our VPC, which we just created. So we can go back to our VPCs and our subnets. Oh, something new that was just released is the resource map. So now we can see all of our resources for our Spoke VPC1. And notice that we have two subnets here, and it will take us to our workload subnet. And notice that the IP address is in the range of the instances in the range of the new subnets that were created. I think this is really cool. I'm glad they created this. This completes our demo. Here I have provided additional information where you can find more about the AWS Transit Gateway, as well as the AWS Transit Gateway Hub and Spoke Terraform module. I thank you all for viewing this presentation, and thank you HashiCorp for having me at HashiTalk 2023. Feel free to connect with me on Twitter and LinkedIn. Peace.